All right, so continuing with our discussion about Stirling's approximation, in statistical thermodynamics, we often have factorials of very large numbers. So for example, we have Avogadro's number and even more numbers of atoms and molecules. As n, or the number of particles, becomes larger, it's going to be difficult to manipulate any of the associated functions where we have things involving the n factorial. Since n factorial is a product, we often find it much more convenient to use the natural log of n factorial, which would then give us a sum. So, for example, n factorial is equal to n times n minus 1 times n minus 2, going to 2 times 1, and so on, right? So, that means that the natural log of n factorial would be equal to the sum on L of m going from m equals 1 to n. Now, even though we're dealing with discrete particles, as the number of those particles increases, we can approximate that sum as an integral, okay, where we have the ln of 1, the ln of 2, and so on, where our ln of x is equal to 1, is equal to 2, is equal to 3, and so on. If I add up all those pieces, I will eventually get my overall function for the natural log of x. So that means that the natural log of n factorial, which we said was the sum over m equals 1 to n of ln of m, that is then approximated as the integral of that function going from 1 to n. And so therefore the natural log of n factorial is approximately equal to n times the natural log of n minus n minus 1. So for large values of n, we are going to then be able to obtain Stirling's approximation, because as n becomes very, very large, subtracting off that 1 isn't going to be a big deal, and so therefore the ln of n factorial is approximately equal to n times the natural log of n minus n when we have large numbers, which again we would have if we're dealing with Avogadro's number of particles. So now that we know Stirling's approximation, we're now ready to begin discussion of the multinomial distributions. So let's say that we have 4 students and 4 seats or places that they can be. All right. If I am filling my first seat, okay, then there are 4 different students that can take that first seat. Okay. Once I've filled one of those students into the first seat, let's say that I put student 4 into that spot. Okay. Well, once I've put one of my students in the first seat, then when I go to the second seat, okay, then there are only 3 other possible students that could take that spot. Okay, so let's say that I picked 2. Okay, so now student 4 is sitting in seat 1, student 2 is sitting in seat 2. Okay, so now I've taken up 2 of my seats with 2 of the students. So now that 2 of my students are sitting, only the last 2 students could take that third seat. All right, so let me pick student 1. I'll put them in that seat. And that means that now that all of the other seats have been taken, okay, we only have 1 student that can sit in the last seat. So that means that the only possible case for that last student is to go into that last seat. All right. Now, so what does that mean for us as we're counting? Well, what that says is that thus the number of possible arrangements of students is going to be 4 choices for the first seat times 3 choices for the second seat 2 choices for the third and 1 for the last. That means that I will have 4 times 3 times 2 times 1, or 4 factorial. Okay? So, thinking back to our example, right? For n objects, that could be particles, molecules, students, okay? For n objects, we are going to have n factorial configurations. All right? Now, let's take things a step further. Okay? And let's say that we can have different subgroups. Okay? So, for example, let's say that we have 3 juniors and 1 senior for the 4 students. All right. If that is the case, right, then we're going to essentially be binning or grouping our students into particular subgroups. All right? So that means that for the seniors, right, we had 1 student. And for the juniors, we had 3 students. Okay? So if I were to figure out how to arrange my students into bins, then that means that we will have 4 factorial total configurations for our students. Okay, that's our number of students, divided by the individual subgroups as factorials as well. So I've got 4 factorial divided by 1 factorial, which is my seniors group, times 3 factorial, which is my juniors group. Okay, so that would mean that I would have 4 times 3 times 2 times 1 divided by 1 times the quantity 3 times 2 times 1, which means that I will have 4 possible configurations. Okay, so as an example, okay, let's say that we have 4 spheres or 4 balls, and we have 3 that are red, and we have 1 that is green. Okay? If I have 4 balls and I want to look at all the possible arrangements, okay, then I have the case where my first 3 are red and my last one is green. Okay, I have the case where my second to last one is green. I have the case where my second one is green, and I have the case where my first one is green. There are only 4 possible places that I could put my green ball into different possible arrangements. Okay, notice that for 4 balls, when I have the different subgroups, when I choose something about them that's an individual marker, then that means that I am specifically choosing to limit my possible arrangements. Okay, there are 3 factorial ways that I can arrange the red balls, okay? But there's only 4 possible places that I can put the green balls and have a unique configuration, okay? All right. So in general, for n possible objects, okay, with a binomial set, that means of 2 options, okay, then that means that I will always have n factorial, which is my total number of particles factorial, divided by however many are arranged into each of those 2 subgroups. So I would have n in subgroup A factorial times n in subgroup B factorial, okay? Now, since it's a binomial distribution, okay, I could also write this as n factorial divided by n A factorial, okay? And once I choose how many are in the first group, then we know that the total minus that many will give me the same thing as my second group, okay? So we can write it that way. You can think back to, how mole fractions work for binomial mixtures or for binary mixtures, okay? Now, let's consider the binomial expansion okay, where we have x plus y to the n, okay, and that's equal to the sum on n1 equals 0 going up to n, okay, and that is equal to n factorial times x to the n minus n1 times y to the n1, all divided by n1 factorial, n minus n1 quantity factorial, okay? Now, notice that n factorial divided by n1 times the quantity n minus n1 factorial, all of this that sits out front, that is our binomial distribution, okay? So I could also write this as, let's do it in blue, I could also write this as the sum over n1, then the sum over n2 to the star, where I then have n factorial times x to the n1, y to the n2, divided by n1 factorial times n2 factorial, okay? And that star, it just means that we're going from n1 plus n2, and those have to go all the way up to a total of n. So essentially, I'm just looping over all the possible values of n1 and all the possible values of n2, making sure not to double count. All right? Now, we can then expand this as a multinomial where we have as many possible bins as we want, right? Because there could be an infinite number of possible arrangements for these different subgroups. So, expanding this to a multinomial distribution, we then have the quantity x1 plus x2 plus x3 going up to x sub r raised to the n. Okay, that is going to be equal to the sum on n1, n2, n3, all the way up to nr, going up to the star, where again, the star just means that the overall sum of these sum values on n needs to go up to our total number of particles. And then this is over n factorial times x sub 1 to the n1, x sub 2 to the n2, all the way up to x sub r to the nr, all over the product from j equals 1 to r of n sub j factorial. All right, now this piece out front, if this was our binomial coefficient, then that means that this must be our multinomial coefficient. All right. In our next video, we're going to talk about the method of Lagrange multipliers.